This video is an introduction to the muon decay lab, or muon physics lab, for the intermediate lab in spring of 2017. The learning outcomes for this lab are to become familiar with the scintillator operation and what that means, and then to measure the decay lifetime of elementary particles. The two lab objectives: one is to acquire a histogram of muon decay times with a simulation program and analyze that information. And the second is to define the decay lifetime of muons by collecting actual detector counts and fitting it to an exponential decay. So there are interesting questions that elementary particles pose. And muons are a great source of questions and answers. There are some statistics. So about 10,000 muons per square meter reach the surface of the Earth. Muons are generated, see in a moment, with, well, at the bottom here, we see that a proton goes through the upper atmosphere, and one of the things that happens is it creates a muon by collision with other particles, and then those muons travel to the surface of the Earth. The question is, though, these muons don't survive for very long. So how do they make it to the surface of the Earth? You make like many particles very, very far away from the surface, and they only have a half-life of about 1.5 microseconds, but we still get the majority of them, in fact, almost all of them make it to the surface. So these two questions: how can the particles make it to the surface of the Earth? And two, how do we measure the muon lifetimes? We're going to do the muon lifetime measurement in this lab, and we're going to think about the answers to how particles make it to the surface of the Earth. So to answer that question, we need to do a quick review of special relativity. This is assuming that you've had some special relativity in your coursework already. So as a reminder, in special relativity, there are two common phrases. One is time dilation, and the other is a length contraction. And the common kinds of pictures you'll see are something like a moving observer on a rocket ship who has, I love the stick figure eye, the moving observer is traveling with a very, very fast speed, something close to the speed of light, and the time measured by the moving observer and the lengths measured by the moving observer will be different than those by the stationary observer. The thing that's the same in both cases is the speed of light. The speed of light is always c, and the thing that's also the same is the actual speed that's measured for the moving object. So this time dilation and length contraction. Time and length are changed by the Lorentz factor gamma. Gamma is equal to 1 over the square root of 1 minus v squared over c squared. And you'll notice that gamma equals 1 when v equals 0, the speed of light at which you're traveling. And gamma, if v becomes larger, in fact, if v became close to c, then v squared over c squared becomes close to 1, and gamma gets quite large. So this Lorentz factor comes into play when looking at the change in times and change in lengths. Time dilation, you see here that the delta t and delta t naught are related by a factor gamma, and L naught and L are also related by a factor gamma. I want to remind you what those delta t naughts and L naughts are. In this case, the delta t naught is what's called the proper time, and L naught is what's called the proper length. So we're going to look at that for the muon situation. In the case of the muons, the proper time is the time for which the start and finish of two events happen in the same place. In other words, for the muon leaves the Earth's upper atmosphere and arrives at the surface of the Earth. Relative to the muon, those things happened in the same place, at the muon. Therefore, the muon is the thing measuring the proper time. The muon lifetime is then what we would call the proper time in this case. The proper length is a distance measured in the stationary reference frame. In other words, it's the actual distance, in this case, from the atmosphere to the Earth. So the proper length is virtually always the actual physical distance, not the contracted length. So pictures like this from hyperphysics help to go through what's happening with the muons traveling through the atmosphere, and given a certain speed, close to the speed of light, what's the factor gamma? You can see that here. And how does that change the time that it takes the muon to travel to the surface of the Earth? All right, so we've talked about these muons, but what we're going to do now is we're actually going to deal with detecting them. So our muon detection system, and I encourage you to look at the muon physics conceptual introduction for more details. In the muon detection system, we start here. We've got a little red muon, and it goes through a plastic scintillator. It then creates a photon, in other words, a little signal of light, which goes through a photomultiplier tube, and that generates an electron, which is then detected with some kind of data acquisition. Our specific system looks like this. Our muons travel into the scintillator. Scintillator then generates light, and the light is collected, the little flashes of light are collected by a photomultiplier tube. Now, this photomultiplier tube is powered with a high voltage. The photomultiplier tube creates a little pulse like this, which then goes through an amplifier, becomes a larger pulse, and is then sent through a discriminator where you compare the amplifier or the pulse size with a reference size. If it makes it over that reference size, then you get a nice little square pulse as the output, and that eventually comes out through our USB port to our computer. So what do we expect to see given in that detector? Our decay lifetime for the muons in a scintillator are given like this. A decay lifetime for any elementary particles is something like this, where n of t is the number of muons after a time t, and that's equal to n naught, or your starting number of muons, e to the minus t over tau, where tau is the lifetime, plus b are background counts. So tau is the muon lifetime, b is the background detector counts. And it's been measured pretty well that the muon free space lifetime is 2.197 plus or minus 0.001 microseconds, so approximately 2.2 microseconds. All right, let's review a little bit of exponential decay. That expression, n of t equals n naught e to the minus t over tau, comes from this. Comes from this differential equation for exponential decay. So if dn dt goes as minus lambda n, then we can integrate that, and we get n of t equals n naught e to the minus lambda t. That's almost the same as what we saw. And in fact, so that plot, or that expression, will give us a plot like this on the right. This is just an example of muon lifetimes from a particular source. The lambda here is our decay constant, but the expression that I showed you a moment ago was in terms of the muon lifetime. So let's relate the decay constant to the muon lifetime, or the mean lifetime, both ways. Tau is equal to 1 over lambda. So pretty simple that we end up with the expression e to the minus t over tau instead of e to the minus lambda t. So now we've got something like this. You will collect your muons. They will arrive with energies that make them build up counts in the scintillator with different decay times. And the amount of time that it takes them to decay in the scintillator is the same as the amount of time that it would take them to decay anywhere else. So we have enough low energy muons that decay and actually stop in our scintillator to give us this information. The conceptual introduction, again, gives you much more detail on what all this means, and please reference that for more information. In this experiment, we're going to do two things. First, we're going to run the muon simulation program, and it was described briefly in the how-to video. And then you'll actually acquire the muon signal. So watch this video for this portion of the video for the equipment in the experiment. In this section, I'll describe the equipment for the muon physics experiment. The setup is as the picture looks, pretty much. The primary part of the setup is this cylinder, and inside there's a scintillator detector, and there's some outputs and power inputs and stuff. It's all very contained just in that cylinder. And in addition, we have an electronics box behind it, an oscilloscope that we'll use to look at things off and on, and the computer. And the computer will be a primary part of this experiment. So to get started, we turn things on. You can first turn on your scope with the power button right here, and that'll warm up. The power switch for the electronics is in the back. Turn that on. You'll see a little red light showing that AC power is on. And now that's about all that you have to turn on. Log into your computer. To start detecting muons, because remember that muons are just floating around all the time. To start detecting them, we simply turn up the high voltage adjust. So we're going to turn up the high voltage adjust to, I don't know, around 8, somewhere pretty high, 8 or 10. And what you'll start seeing is that on this muon physics box, the electronics box, you'll see a little muon detected light flickering. And that means that our muons are being detected. In order to see that, you'll notice that the output from the photomultiplier tube, or PMT, is connected to the PMT input. If you want to hear these little muons being detected, so if you turn down the power, not very many, turn up the high voltage power, get more. And that's just a little audio switch to hear the muons. All right, so we can look at an individual pulse. When the muon is detected, it creates a pulse, and that's what's building up here on the scope. Gives us a little bit of information, just that the muons are actually there, but the information from the box is even better. Right, so we are now running. The muons are being detected, and now we want to collect them. So the collection is what's going to give us our decay curve. On your desktop, you'll find two things. There should be a couple shortcuts. If not, your lab instructors will help you find them. There's a muon simulation shortcut and a muon shortcut. So the first thing you're going to do in the first lab objective is to run the muon simulation, where you simply open the simulation, say start, and then it starts acquiring data that is as if there were actually muons being detected. So you get a sense of what you expect to have happen, you can analyze it, etc. I'm going to quit out of that. And instead I'll open the muon shortcut. So this is the actual muon physics collection. This is connected to by a USB cable connected to the photomultiplier tube output. And first thing we're going to do is configure. Select COM5. That'll read off of the USB. And then we can just say start. There will be, expect to play with this a little bit. So already I'm starting to see some counts, which is good. We can see more counts by turning up the voltage. It's pretty much up at the max. Or turning down the discriminator. And we'll collect more quickly as we make those changes. All right, so now we just wait. Just sit and watch your muons being collected. After a while, you'll start to have an appropriate exponential decay curve. After detecting your data for a while, you can then select the fit option, enter the password that is given to you in your lab instructions. And this will usually work. Right now I'm getting a divide by 0 error, which just means there aren't enough data points here. And that's it. And the rest of the experiment is about analyzing the data that you acquire. Here's a couple reminders after that section of the video. First, you're going to turn on different power switches. Second, you set the high voltage adjust on the scintillator tube to between 8 and 10, the numbers 8 and 10, which actually refers to something like minus 1100 volts. Then connect the photomultiplier tube output on the detector to the photomultiplier tube input on the electronics. On the computer, open muon.exe. Configure, go to Configure and select COM5. That'll talk to USB. Then hit Start. And in order to fit the data, ask for the password. And just hit Fit, and it'll give you a nice fit, which will give you an approximate lifetime of the for your muons. For the pre-lab questions, think about your understanding of special relativity and determine the distance that the muon travels in the muon frame of reference. So given that the speed of the muon is the speed of light and the proper distance is 50 kilometers and the muon proper time is 2.2 microseconds. Then make a sketch of the plot of detector counts versus time that you think that you'll see when the detector is recording muon signals. Be sure to put a scale on the time axis, but it is not necessary to put a scale on the counts axis. Getting started has the usual instructions, and we'll talk about diagrams. Diagrams are your most important thing here, and as you do this lab, you'll need to think about what is necessary to include in your diagram and what just adds unnecessary information. And that's all.